Good morning, my dear students. Welcome to the chemistry class. Today we are continuing the integrated rate equation. Yesterday we saw about the integrated rate equation for zero order reaction, and today we are calculating integrated rate equation for first order reaction. So look here integrated rate equation for first order reaction is nothing but the order of the reaction is 1. It means when the rate expression, the power of the concentration of reactant should be 1. It may be a overall sum should be 1, or if the reactant is only 1, then the power should be the 1. Together, whenever we are observing the total power of the concentration of the reactant should be 1, then it indicates that order of the reaction is 1. So we will begin the derivation of integrated rate equation for integrated rate equation for first order reaction. So this derivation will ask for 3 marks. It is also important. Let's begin. Consider a reaction. It's a general reaction when the reactant is going to form the product. R is nothing but reactant, A is the product. If it is first order reaction, then we will say that according to first order reaction. If the reaction is said to be first order, then we may say rate of the reaction for this general reaction is rate is equal to concentration of the reactant should have the power 1, whereas K is the rate constant. Rate is equal to K, rate constant, into concentration of the reactant raised by the power 1. That power 1 indicates that order of the reaction is 1. If it is 0, 0. So we know that rate expression can be written in the form rate minus dr upon dt, means rate of the reaction, it is with respect to the concentration of the reactant. We can represent rate is equal to minus dr by dt. We will substitute this one in this reaction, whereas rate is nothing but minus dr upon dt. Rate is equal to minus dr upon dt. K as it is rate constant. R raised to 1 is nothing but anything raised to 1. The base remains as it is. Therefore, concentration of the reactant is same as it is. So again, by this expression, we will be continuing. On rearranging this equation, we are setting dt to the right side and we are taking r to the left side. On rearranging the whole equation, we are going to get minus dr. We are taking this r to the left side. Minus dr upon r is equal to, we are sending this minus to the right side. It becomes minus k into this dt to that side into dt. Dr by dt, dr upon r is equal to minus k into dt. Dr upon divided by r is equal to minus k into dt. So to this expression, we are going to introduce the integration. On integrating both to the side. So on taking the integration on both the side, left and right, it becomes minus. So here minus is in the right side. This is the integration symbol. Differentiation of r divided by r. T r is nothing but differentiation of r divided by r. Minus k, it is a constant, it is taken outside. Integration of t. Can see here, I applied integration to the left side and to the right side. Minus k is a constant, that's why I have taken separately. Minus k integration of dt. So we know that integration of 1 by x dx is equal to log x. Actually it is a log x, but we are considering that as a log we are initially writing in the chemical representatives. Generally, instead of taking the log, we are writing ln, and later we are converting that ln into the log. Here it is ln x. Integration of dx by x is equal to log x. We know that according to the integration formula, but here we are writing the ln x. Integration of 1 by x into dx is equal to ln x. Here integration of 1 by r into dr is the same expression here. That's why we are writing it as ln. Instead of x we are having r. Ln r is equal to minus k as it is. Integration of dt is t plus I, where I is the integrational constant. Are you getting this expression? I am writing based on this integration of dr by r is nothing but log r. We are writing that as ln r. Later we are converting that ln r into the log r. Ln r is equal to minus k as it is. Integration of dx is x. Similarly, integration of dt is t plus I, where I is integrational constant. Where I is integrational constant. It is an integrational constant. To calculate I value, or to get the I value, we have to substitute. What we have to substitute? It's the same thing which we did in the zero order reaction. To calculate I value, we will take t is equal to 0. The condition is we are taking t is equal to 0. When t is equal to 0, R becomes concentration of R. Here 0 time indicates that the reaction is not at all started, means it is in the beginning. Therefore, concentration of R becomes initial concentration. It becomes R0. By substituting this in this expression, we just take this one as equation number 1. By substituting in the equation number 1, we are getting ln R. R is, we have to take that R0. Ln R0 is equal to minus k into t. Minus k, here t is nothing but 0. If anything into 0 is nothing but 0, therefore minus k into 0 is nothing but is totally 0 plus I. I is written as it is. Therefore, I is equal to, we are getting I is equal to ln R0. I is equal to ln R0. We just take this equation as equation number 2. So now what we have to do? The same thing what we have did in the last class, that is we are going to substitute this I value in the previous equation. Substitute equation number 2 in 1, or substitute value of I in the above equation. So we are getting a ln R as it is. Ln R as it is equal to minus kt. It is, this one is also as it is, minus k into t plus I. I can be written as I value is ln R0. Therefore, I is nothing but ln R0. So here we are rearranging this expression. We are taking minus k to this side and we are sending ln R other side, because we are going to calculate the integrated rate equation for first order. Means integrated in the rate equation, we are calculating the rate expression of this equation. Means we need k. K is equal to, in that way we have to generate the equation. Therefore, minus kt coming to the left side, minus kt becomes plus kt. K into t is equal to ln R0 as it is. Ln R0. This ln R, when it moves to the right side, plus becomes minus. Minus ln concentration of the reactor. Here I am sending t to that side because I need k value. K is into, when it moves to the right side, it becomes divided by 1 by t. Look here, ln R0 minus ln R means we will know that log A minus log B, becomes log A by B. I hope you remember this expression. Log A minus log B. Log A minus log B can be written as log A by B. Similarly here, ln R0 minus ln R that can be written as ln R0 by R. The same expression I am using here. Ln R0 divided by R. Now we are going to convert the ln in the form of log by taking some constant, that is ln can be converted as ln x. To make it as log x, we have to multiply the 2.303 log x to the base 10. Look here, to any of the ln value, ln x, generally I am taking ln x. To make it as a log x, we have to multiply the log x to 2.303. It is a constant term. It is a conversion of ln to the log. Therefore, here we are converting k as it is 1 by t to convert ln into the log 2.303. It's divided by t. Ln becomes log to the base 10. Remaining is as it is R0 divided by R. R0 divided by R. This is the expression for integrated rate equation for first order reaction. So here k is equal to k as it is ln is converted as ln by writing 2.303 means multiplication in the log 2.303 log R0 by R to the base 10. Here k is the rate constant, t is the time, R0 is the initial concentration and R is the concentration of the reactant at a time t. So soon after writing this last expression, you are not supposed to forget the statement or the meaning of the terms in the final equations. I hope you feel it is easy. There is no much difficulty, and the zero order and first order reactions, they are similar to each other. Only thing is we should know first order is nothing but power should be 1 and zero order is reaction is nothing but the power of the concentration of the reactant should be 0 for zero order, 1 for first order. Are you getting? So this is the expression. This is important for 3 months. You may get the question either zero order, if not it will be the definitely first order. It is a fixed question. Now we are seeing the examples for first order reactions. So here the first one is the decomposition of nitrogen pentoxide is an example for first order reaction, and second one is decomposition of dinitrogen oxide is also follows the first order reaction, and all the radioactive disinfections or disintegrations are considered as these are following first order reactions, means order of these reactions are first order. So they may ask you to write the example for first order reaction, or they may give you the example and they may ask you to calculate the or which is the order of the reaction. So these 3 examples, and in the zero order reactions I have given 2 examples. These 2 examples are totally these 5 examples. 5 examples are important for your annual exams, and whichever I did today and yesterday, these 2 are more important for your examination point of view. So without further, do practice. If you feel any difficulty, you just call me or message me. I will clear your doubts. Okay. So now we will see the relation between first order reaction and its half-life. No doubt it is also similar to just what we saw in the last class, that is relation between zero order and half-life. It is now the relation between first order and its half-life. So here, to make the relation between first order and half-life, we may take the final expression of the first order reaction, or it's better to take the previous one, means ln, because in the log it's very much difficulty to convert that as log. That's why if you are taken the first equation, means final equation, if you are beginning this expression by taking the first one, you have to soon after this one you have to convert this one to the previous one. Therefore, directly I am taking according to the first order reaction. According to first order equation or first order reaction, K is equal to 1 upon T ln R naught divided by R. Means here I am taking the ln expression instead of log. There is no difference, both are same. So here this expression is the first order kinetic reaction. So here to calculate to make it as a zero order reaction for half-life relation, half-life of first order reaction. To make this first order reaction as a half-life reaction, we have to substitute what we have to substitute. T, we have to form that T in the form of T half, then only the reaction time becomes half-life of the reaction. T, we have to take T half. When we have taken T is equal to half, then concentration of the reactant becomes half of the initial concentration. When T is equal to T half, then R becomes R naught upon 2. Means half life of the reaction is nothing but it's a time duration at which the initial concentration of the reactant is reduces exactly to half of its concentration. And the time is called as half-life. So by substituting these two in the equation number 1, so K as it is 1 upon T becomes T half into ln R naught as it is, because we have to convert R into R by here R. Therefore, this R becomes R naught divided by 2. This is whole divided by, and this is R naught by 2. So now we will take this one as we are setting T half to the left side and taking K to the right side. Can you see here? T half in the numerator. Denominator, we are setting that to the numerator. Therefore, what happens? By rearranging the equation, rearranging equation, by rearranging the equation, T half becomes T half is equal to 1 upon K. K comes this side. 1 upon small k into ln. Here can you see R naught divided by R naught by 2. This R naught cancels. This 2 moves to the right side. How means? Can you see here? A upon B whole divided by C upon D. In this term, A upon B remains as it is, and C upon D, which is in the denominator, it will move to the D to the numerator. Means A upon C. It's a mathematical expression. A upon B whole divided by C by D is equal to A upon B into D by C. This C by D is inversely taken as D by C. The same expression here also. R naught divided by R naught. This R naught will cancel and 2 move to the right side. It is in the form of D. 2 comes to the up. Therefore, ln R naught cancels each other and remaining 2 moves to the up. Ln 2. Therefore, T half as it is 1 by K is as it is. We are converting ln 2 to the log. Therefore, it becomes 2.303. Ln becomes log 2 to the base 10. But we know that log 2 is having the value 0.3010. log 2 is having the value 0.3010. Therefore, we will put that value. T half becomes 2.303 into log 2 value is 0.3010 whole divided by k. By multiplying this, we are going to get T half is equal to 0.693 whole divided by small k. This is the final expression to interrelate the first order reaction and its half-life. So, just look here, T half is nothing but half-life of reaction. It is for the first order. In the first order, half-life is nothing but 0.693 divided by k. Here T half is nothing but half-life, k is nothing but rate constant. This is first order reaction. Just you recall the half-life of zero order reaction. In the zero order reaction, the expression was, just I am writing this to compare, it is R0 divided by 2k. This is the expression for half-life of zero order reaction, and this is the expression for half-life of first order reaction. Means half-life of zero order reaction is depends on the initial concentration of the reactant, whereas half-life of first order reaction is independent on the initial concentration of the reactant. This is important. They may ask the applied question for 1 month. Write the half-life of the reaction or the half-life of reaction which not depends on the initial concentration, that is first order reaction. The first order half-life is independent on the initial concentration of the reactant, whereas this depends on the initial concentration of the reactant. Are you getting my point? T half is half-life, K is the rate constant. So this is important for 2 marks. The integrated rate equation for zero order is asked for 3 marks, and similarly the relation between first order and its half-life will be asked for 2 marks. If they ask together, it will be for 5 marks. These two are important for your annual exams. I hope this is clear for you, and I am sending the notes in the PDF file, and just to note down the notes and write the assignments. The assignments are given in the below, and those who have written that notes, just to text me to my WhatsApp number, and if you are having any doubts, ask me, or you can call me and ask your doubts. Okay, we will meet in the next video. Until, have a nice day. Bye.